so my screen is visible. Am I audible to all of you?
Yes, sir.
Okay, so good morning. So can we start the class? Are you all ready?
Yes, sir.
Okay, fine. So how are you all
Yes.
finding the classes? We have already done something like 2 weeks of classes now. How are you all finding it? How many of you are attending from the beginning? Must be a lot, right? Okay, yeah, thank you. So some are basically informing me via the chat. That's fine. I think all your mics have been muted, correct? Prajwal, can you unmute them so that they can interact with me?
Hello.
Okay, so you all, if you want to talk to me, you can unmute and then talk to me. All right. Fine. So let's actually begin the discussion. Today I'll be looking at the concept of conservation of momentum, and collision. Okay, so let's see what are the different things that we need to actually worry about here. As I usually do, we'll have a quick recap of all the important and the problem types and then solve. So I will stick to my method. I will first start with the brief synopsis of all the important ideas. From the previous chapter in the second law of Newton, we have seen that F is given to be dp by where P is the momentum of the particle, is the moment of the particle. Now you can actually write this as F dt is equal to dp, or dp delta p can be written as integral f dt, integral f dt. This idea is called impulse momentum theorem. Okay, this term integral f dt is called as impulse. Okay. Now, whenever you want to basically find out what the change in the potential energy is, change in the momentum is. I've been teaching potential energy all these while, so I just think change in the momentum. Then there's a relation between the change in the momentum and the impulse. This is what is given to be. Okay. Now, oh, by the way, you should know what momentum is. Momentum is mass into velocity. Mass into velocity. All right. So you can always find out the change in the momentum. If you know integral f dt. Now I've seen many problems where they give you what is the force and also the time for which it is acting. Then you have to find out what the change in momentum is. So if f is constant, which happens in many cases, then delta p can simply be written as f into delta t. F into delta t. All right. If it becomes very simple expression, if f is constant. Here, point to be noted is if I have a plot of force versus time. Okay, if I have f versus t to be given something like this here, like this, then the area under this curve will always give me integral f dt. So what are the area under this curve also gives me? Gives me delta p, which is the change in momentum. Okay. Now, third point to note here is if f is 0, then what happens is integral f dt will be 0, or that will actually lead to an idea called delta p is equal to 0. So even delta p will be equal to 0, which implies the final momentum minus initial momentum is equal to 0, or final momentum is the initial momentum. And this idea is what is called conservation of momentum. Okay.
Sir, can you mute the message sound, sir?
Message sound, I think you should mute in your system, because in my system message sound doesn't come. So it's individually, you'll have to do it in your system. So make sure that the notification for the message just appears. There's no sound there. Okay, remove from your system. All right. So when the force is 0, by the way, let me just add one point here. It is the external force that we are all talking about. If the internal forces are present, I don't have to really bother much. So I will basically add this external force for everything here. Okay, that is what is missing. It should be external force into dt. External force into dt. Have you all written down this? Can I go to my next page?
Yes, sir.
Yes, sir.
Yes, sir.
Sir.
Thank you. Yes. Okay. Now, you do have several examples where the external force will be absent. External force will be 0. Only internal forces act. Now, what is the meaning of internal forces? Okay, just to give you an example for this, if I have one body here of mass m1, okay, moving with some velocity, and hits another body of mass m2, when they both are in contact, you all know that there will be a normal force acting on it. N1 here, N2 here. This N1 will be equal to minus N2. They are called action and reaction pair. Now, this action and reaction pair, the forces in fact are called internal forces. Internal forces, because both action and reaction are acting on the same system, not on the same body, acting on the same system. Now the system here is together, M1 and M2 is called as one system. On this system, we have force N1 and N2 acting, and therefore this is called as internal force. So when only internal forces are acting and the external force is 0, we always say that the final momentum will be equal to the initial momentum. So an extremely good example where the conservation of momentum will be valid is in the case of collisions. Okay, so therefore we'll take this as an example and then try to understand more about these collisions now. Okay, now I think most of you know, whenever actually one particle collides with the other, the forces are purely internal. Whatever be the type of collision, okay, N1 will be equal to N2 minus N2 rather for all kinds of collision. All kinds of collision, this must be valid. Whether it's elastic, inelastic, plastic, 1-dimensional, 2-dimensional, and so on and so forth. You will always say that n1 will be equal to minus n2. Okay. Therefore, conservation of momentum is valid in all cases of collision. All cases of collision. A very, very important point to note. A very, very important point to note. Now, we shall understand more about this particular collision now in detail. Look at it. For a mass m1, let us say, is moving with an initial velocity u1. See, whenever I put something on the top, this will be my initial velocity. Then another body of mass m2 is moving with velocity u2. If u1 is greater than u2, because they both are moving in this direction, u1 is greater than u2, then collision is possible. Okay, you will find that this u1 minus u2, which is the relative velocity between the two, is called as the velocity of approach. Is called velocity of approach. Then, once they both collide, they will start now moving with different velocities after the collision. Okay, this was the story before the collision. This is the collision. This is the story after the collision. After collision, this will now move with a velocity v1. This will now move with a velocity v2. Masses are m2 and m1s, or whatever I have taken the earlier. Mass will not change, but the velocity will change. Now, generally after collision, you will find that v2 will be greater than v1. If v1 is greater than v2, then both of them will be moving together. If you want them to collide only for a short duration of time and then move, then v2 should be greater than v1. Then v2 minus v1 is called velocity of separation. It's called velocity of separation. Now, one point I want to add here is during the collision, okay, the time of collision is supposed to be very small. Very small. Switch off your mic. Switch off your mic. It's going to be difficult otherwise. Switch off your mics. Switch off your mic. I'm going to my next page. Hey, please switch off your mic.
Greater than v1. v2 minus v1. Separation.
This is called velocity of separation. Okay, I'm now going to my next page. If you all have done this. Have you all written down? Please switch off everyone, sir. Please mute the mic. Prajwal, please mute the mic of that person. FD595E. What you can be very sure is, in any kind of collision, what you can be sure is that conservation of momentum is valid. Momentum is valid. Then what it implies is m1u1 plus m2u2 is equal to m1v1 plus m2v2, because the initial momentum should be equal to the final momentum. This is a very important idea which is always valid. One more also is valid. This is called as Newton's law of collision. Newton's law of collision will be very, very useful for solving problems. What does it say? It says that the velocity of separation is proportional to the velocity of approach, which is V2 minus V1 is proportional to U1 minus U2. Now, the proportionality sign can be replaced with a constant, which is given to be E, where E is called as the coefficient of restitution. Is called coefficient of restitution. Now, E is a very peculiar value. E will remain as a constant for a given, say, pair of objects. It will depend on the objects, what is it made up of, and so on and so forth. So it remains constant only for that particular collision. Now, if E is equal to 1, what is the collision called? If E is equal to 0, what is the collision called? If E is between 1 and 0, what is it called? Okay, when E is equal to 1, it is called as perfect elastic collision. When E is equal to 0, this is called perfect plastic collision. Somewhere in between, this is called inelastic collision. So there are three types that you need to worry about: perfect elastic collision, perfect plastic collision, and also inelastic collision. You will find that in the first case of perfect elastic collision, the velocity of separation will be equal to the velocity of approach. Okay, velocity of approach. Now, if you have two bodies colliding in this way, like I took the other time with initial velocity u1, this is with velocity u2, m1, m2, and then after that it has a velocity v1 after final velocity v2, then you can show that by using this equation 1, okay, this equation plus the other equation. What is the other equation? m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. With these two equations, you can show that v1 will be equal to 2 times m2 u2 by m1 plus m2 plus m1 minus m2 by m1 plus m2 into u1. So I'm writing v1, that is velocity after the collision of the first body, will be given by this expression. In most of the problems, you have to find out what v1 and v2 is. So I think this will be a useful expression for that. Similarly, v2 will be given as 2m1 u1 by m1 plus m2, okay, plus m2 minus m1 by m1 plus m2 into u2. Okay. So this is for case 1, which is called perfect elastic collision, or simply they call it as elastic collision. These two expressions are going to be very, very useful. Let me make some note for case 1. Now look at it. If m is very large when compared to m2, but also we'll take u2 to be 0. That is, you only have first body moving with velocity u1. Okay, the second body is at rest. The second body is at rest. Then look what happens to this expression. Okay, now v1, if m1 is very, very large when compared to m2, v1, the first term will be 0 here because u2 is 0. And then I have m1 minus m2 by m1 plus m2. This can be roughly be written as, because m1 is much greater than m1, so m1 by m1 into u2. I'm neglecting m2 in front of m1 because m1 is much larger than m2. So which implies that v1 will be equal to u1. If m1 is very large when compared to m2, there is no effect for the body of a larger mass. It simply continues to move with the same velocity. Now, what will happen to v2? v2, on the other hand, will be interesting to see here. This will be equal to 2 times m1 divided by m1, because m1 is very large when compared to m2. I neglect m2 into u1. Second term is 0 because u2 is 0. So which will turn out to be approximately equal to 2u1. Very interesting to see what will be the velocity of the second body will be equal to 2 times the velocity of the first body. Okay. In fact, we call this basically a case where you actually have a lorry or a truck moving with some velocity u1, and there is a bicycle standing here. Okay, a bicycle here standing here with velocity equal to 0. When this truck comes and actually collides with the bicycle, this is what exactly will happen. Truck will continue with the same velocity, but the bicycle will get twice the velocity. This you can keep it, in fact, as an information. When you solve problems, you can very quickly arrive at the answer, because the smaller body will always have twice the velocity of the bigger body. All right. Same way. Note 2. We will say that now m1 is very small when compared to m2, and also keep m2 at rest. Same problem, but only thing is I'm making m1 actually smaller when compared to m2. So this is a case when you have actually like a ball coming and hitting a wall. Wall essentially has m2 is very, very large when compared to m1, isn't it? Okay, so mass of the ball, in fact, is very small. Let's take it as m1. In that case, see what happens to the results that you have obtained. Okay, v1 will now be equal to u2 is 0, so the first term is 0. The second term will now become m1 is very small when compared to m2, so minus m2 by m2 into u1. In other words, v1 will be equal to minus u1. So this ball, when it comes and hits the wall, will get rebounded back with what? With the same velocity. This is coming with u1 here. Ball will rebound with same velocity u1 in the opposite direction. All right. So there's no question of now velocity for the second body. Look at it. What will happen to v2? For v2, the first term will now be 2m1 by m2. I've neglected m1 in front of this, into u1. If m2 is very large when compared to m1, then m1 by m2 will be negligible. When compared to 1. So will be almost equal to 0. Okay. Therefore, I say that v2 will be equal to 0. Wall will not move. No, after collision, you can't expect wall to move. So if you have one mass very, very heavier than the other, this is what in fact the situation is going to be. Third note, what will happen if both of them are of the same mass m? Okay, and it's a very interesting collision to understand. Here you will find that v1 will be equal to 2m by m plus m into u2 plus m minus m divided by m plus m into u1. So this part is 0. And what do you get this to be? You get U1 to be equal to U2. And interesting, isn't it? The second body will have the velocity of the first body. Similarly, what will happen to V2? Now V2 is given to be, what is the expression for it? 2m1, okay, by m plus m into u1 plus m minus m divided by m plus m into u2. So this part again is 0. So what am I left with? I'm left with the expression for V2 as simply u1. So the second body has acquired the velocity of the first body, and first body has acquired the velocity of the second body. So here we say that the velocities get interchanged. Gets interchanged. A very important idea. I hope you all are able to understand that. Okay. Now someone is saying that these formulas are similar to that of reflection of waves. Very true. Instead of say masses, you will have velocities like that. So 2v1 by v1 plus v2 and so on and so forth. You're right. I think only one term is there. There's no second term there. Oh, second term is also there. No? This is what it is. Can I go to my next idea? If you're all written down this, can I go to my next idea? Yeah. Can we move on? Okay. Now we will look at the second type of collision. What is the second type of collision? Is the plastic collision. Now this is case 2, right? Case 2, plastic collision. In plastic collision, E is equal to 0. So what is happening to the velocity of separation, therefore, will be equal to 0 times the velocity of approach. So therefore, V2 minus V1 is equal to 0. In other words, V2 will be equal to V1. I think now you understand why this is called plastic collision. Very interesting. One body here is that comes and hits another body here of mass m2. Then after the collision, they both will start moving together. M1 plus M2 will now start moving together. They both are like one body now. So they both move together. Both move together in the plastic collision. So if you want to solve the problems on this idea, it's very simple. All that you have to do is use the conservation of momentum. Okay, if this is moving with velocity u1, this is moving with velocity u2. Finally, after collision, they both will move with velocity v. Then you will find that in this case, m1 u1 plus m2 u2 will be equal to m1 plus m2 into v. So what is the velocity after collision? Will be m1 u1 plus m2 u2 divided by m1 plus m2. So we just have one single expression for this, which is given by this. So this is the velocity after the collision. Note an important point here. We'll find that in this case, there will be loss of kinetic energy of the two bodies. Okay, and that loss of kinetic energy will be written as Ki minus Kf, which will turn out to be, as you can see here, half m1 u1 square plus half m2 u2 square minus half m1 plus m2 v square. This in fact is called as the loss of energy, loss of kinetic energy in the case of plastic collision. We also further note that the loss of kinetic energy is maximum in case of plastic collision. In case of plastic collision. Okay, you'll have this to be in fact maximum. loss will be there in this case. Yeah. If you all have written down this, I would like to now go to my next page. Yes, can I go to my next page? Okay. The case 3 now will be that of inelastic collision. Inelastic collision. Here, E is actually between 1 and 0. It can actually have value like 1/3, 1/2, 1/3, 1/4 like this. So it can have a value like this, E. This coefficient of restitution can actually have these values. Now I would like to take an example and then illustrate this inelastic collision. Let us say that I have a body of mass m. Initially is moving with a velocity of 8 meters per second. Okay, it comes and hits another body of mass 4m moving with a velocity of 2 meters per second. Okay, if E is equal to half, then question is find velocity after collision of the two bodies plus important loss of kinetic energy. The problems here will be of this kind, where you have coefficient of restitution to be given like this, and then you are asked to find out what will be V1, V2, and also loss of kinetic energy. So how do we solve a problem of this side, of this kind? First, apply conservation of momentum. Remember, conservation of momentum is valid for all collisions, including this. So you get this to be something like 8m plus 8m is equal to m into v1 plus 4m into v2, where v1 is the velocity of this one after collision. After collision. V2 is the velocity of this after collision. After collision. Then what do we get? This will be equal to m. You can cancel off from everywhere here. You get this to be 16 is equal to v1 plus 4v2. Now I need one more equation to solve this problem. That equation will be from Newton's law of collision. What does Newton's law of collision say? V2 minus V1 will be equal to E times U1 minus U2, isn't it? U1 minus U2. And therefore I get this to be V2 minus V1 is equal to half of U1 is given to be 8, U2 is given to be 2, and therefore I get this to be V2 minus V1 to be equal to 6, and then 6 divided by 2 is 3. Is 3. So I have equation 1 here and another equation here 2. I have to solve this simultaneously to get V1 and V2. I don't think it should be difficult for all of you to do this. So this becomes 4V2 plus V1 is equal to 16. The other equation, so this equation I just wrote it down like this. The other equation is V2 minus V1 is equal to 3. Look at this, so simple to do. If you add both of them, you get this to be 5V2 is equal to 19. So what is V2 equal to? Equal to 19 by 5. 19 by 5. 19 by 5. Okay. This will be 4.9, isn't it? This will be 4.9. No. How much will this be? 4. If you do 4, you get 16. 16. Then you have 15. Then you have 4. 4. So this will be equal to 4.8. 4.8. It will be 4.8 meter per second. So what will be V1? We know that V2 minus V1 will be equal to 3. So V2 therefore will be equal to 3 plus 4.8. So which turns out to be 7.8 meter per second. 10.8 meter per second. Yeah. Oh, it's 3.8. Sorry. 3.8. I'm so sorry. So this should be 6.8. You're right. 3.8 is what I should. It should be less than 4. No? Stupid of me. So it should be 3.8 meter per second. This is 6.8 meter per second. Correct. Thanks for that. Very attentive class. Like it. So I have determined both V1 and V2. V2 is to be obtained. My goodness. V1 therefore is equal to V2 minus 3. So V2 is 3.8 minus 3. So V1 will be lesser, will be equal to 0.8 meter per second. 0.8 meter per second. Yeah, V1 will be 0.8 meter per second. Thank you very much. I think that's what the answer is, because V2 minus V1 is equal to this, and therefore V1 will be V2 minus 3. Okay, so I got both the answers with this. What is the second part of the problem to be done? I have to find out what is the loss of kinetic energy. Loss of kinetic energy is Ki minus Kf. I will give the formula and leave it. I think calculation you can do on your own. So half into what is the mass of the first particle is m. I think I just took it as m, isn't it? M. And what is the velocity of this? 8. So 8 square minus half m 4m into 2 square is equal to minus final kinetic energy will be half m into 0.8 square plus half into 4m into 3.8 square. 3.8 square. So do this, then you get this delta K. Okay. So I'm sure that you will be able to work it out and find out for yourself. Simplify this and find the answer. So I have therefore done the problems on all the 3 cases of collision. Now I would like to take you through another important idea in the case of collision itself. Can I do that? Which is again, a lot of times these questions are asked. So therefore I would like to take you to my next page. Can I? Are you all okay with that? Can I go to my next page? Have you all written down? Next one is called as the oblique collision. Oblique collision. Now, what happens in the case of an oblique collision is that I have a body here, and then I'm going to basically make this body of mass m hit the floor at an angle. At an angle here like this. I draw a normal to it and call this angle as theta. Now it is going to hit actually with a velocity u and come and hit it like this here. Now when it hits, at this point, there is a normal force acting when this body basically is in collision. And therefore I can't use conservation of momentum for this case. Now this body, when it rebounds, it can move with a velocity v like this, making a different angle alpha. It's not necessarily that both the angles must be same. Okay, this body basically can move like this. Now this kind of a collision is called as an oblique collision. Here, the center of mass of this is not along the normal, okay, is making an angle with respect to this, and therefore we call this as an oblique collision. In such a case, you can easily show that the components of the velocity, maybe I'll take this as u and then write this as ux and this as uy. Similarly, for the final velocity, I will write this as vx and this as vy. You can show that along the x-axis, Vx will be equal to Ux. There is no change in velocity of this. Okay, there's no force at all to change the velocity, and therefore velocity will remain the same. Now along the y direction is something important to note. Along the y-axis, you will find that Vy will be equal to E times Uy. What is this E? E is the coefficient of restitution. You will also have a minus sign here, because if Uy is like this, Vy is opposite, and you get this to be Vy is equal to minus E times Uy. There's a result, please note down. This comes because of Newton's law of collision. Newton's law of collision gives you this. Now, if I compare the two equations, I get Vx essentially is V sine alpha should be equal to U cos theta. Because this is what, in fact, the expression will turn out to be like this. Similarly, this equation is going to give you V cos alpha is equal to minus E times U. Sorry, this is sine. I'm so sorry. This should be sine and not cos. The previous one should be sine. Both of them are sines. Okay, sine. This should be EU cos theta. EU cos theta. Now, if you take both of them, in fact, if you divide one by the other, then you get this to be tan alpha to be equal to minus tan theta divided by E. Important result. So tan alpha can be written as minus tan theta by E. Since E will be lesser than 1, you'll find that alpha will be greater than theta. Alpha will be greater than theta. Magnitude wise, I'm talking about. Magnitude of alpha will be greater than that of theta. I hope that point also is clear to all of you. Okay. These equations are going to be very, very important. Very, very important. Now let's take up some interesting cases of this. Case 1. If theta is equal to 0, then what happens? The body basically is dropped from a height. It is coming here like this itself. Okay, then it rebounds back. Now, if it has been dropped from a height h, then let's see what happens. Okay, here the velocity, let me take it as u. When it goes up, the velocity is taken as v. You can show that v will be equal to, because now it is only vy, isn't it? Vy will be equal to minus e times uy, or in this case, v will be equal to minus e times u. Okay, the velocity here, but the velocity that it has gained here, which u square is equal to 2gh. Okay, 2gh. So therefore, velocity can be obtained like this. Now, what happens is, after it rebounds, it goes to a certain height here, and let me take this height here as h1. By the way, I'll make this as h0, okay, when it is dropped. So take it as h0. You can also show that v square will be equal to 2gh1. Now, if you take the ratio of the two, you get h1 by h0 will be equal to v square by u square. But what is v square by u square is equal to? V by u is equal to e, and therefore it will turn out to be e square. And hence, h1 will be equal to e square times h0. h1 will be equal to e square times h0. Similarly, after the second bounce, that is, the particle will now come again, collide, and then go up. When it goes up, let's say that this is given to be h2. So h2 can be shown to be e square times h1, or will also be equal to e to the power 4 times h naught. So similarly, after the nth bounce, I can say that hn will be equal to e to the power 2n times h naught. So it will keep actually coming down as it proceeds. Remember, e is a value between 0 and 1, it's a fraction. So h1 will be lesser than h2. H2 will be lesser than h1. H1 will be lesser than h naught. So that is how it's going to be. That's how it's going to be. So this is one case that I thought I should be definitely telling you about. Can we go to another case now? If you all are okay, can we go to the next case? Can we go to the next case? Are you all done? If you all have written down this, I would like to go to the second case. Case 2. Case 2. Okay. Now, the case 2 here is for the case of the projectile motion. So think of a body is projected at an angle theta. Now this is going to come and hit the ground here like this. Now this will have a range. Let me take it as R0. If this is U, you all know what R0 is going to be. R0 will be equal to U0 2 U0 square sine theta cos theta divided by G. Now what happens is this will come and hit. There will be a collision here, and as a result, this will now come up. If this is coming down with velocity u, this will go with only velocity v. So as a result of this, you will find that again there will be a collision, and that will basically make one more projectile motion happen. So now the range is going to be lesser. Because it is losing some amount of energy, it should now, every time when it comes up here, it should occupy lesser and lesser, say, space after that. So the range will become lesser and lesser. Okay, now it can be shown that R1 will be equal to E times 2 U0 square sine theta cos theta by G. So E times, which is essentially equal to E times R0. Similarly, R2 will be equal to E square times R0. R3 will be equal to E cube times R0. So as it actually bounces every time here, it's going to lose that much of energy, and then the range keeps on reducing. Ultimately, it will have no range at all. So it will just come to rest. But this is how the motion is going to be here. Similarly, can we also talk about the time of flight? Time of flight here will be equal to 2 U0 sine theta by G. Now you'll find that the time of flight T1 here will be equal to E times T0. T2 will be equal to E square times T0, and so on and so forth. Now what about the maximum height attained? Maximum height attained will be U0 square sine square theta by 2G. We can show that this H1, the height here H1, will be equal to E square times H0, where H0 is the first one. H0 is this. Okay. Similarly, H2 can be shown to be equal to E square to the power 4 H0. This is like your case 1. Okay. Where the maximum height attained will always be square of the E into that height H0. Okay. This is how I can find out all the different parameters of this projectile motion. Okay. I think I've basically done all the things that I'm supposed to do for this, but maybe I'll spend another 3-4 minutes on explaining you something. But have you all written down this? I didn't even ask you that. Have you all written down? Can I go to my next part? What if theta is 90 degree? Okay. Can theta be 90 degree? can theta be 90 degree, and what will happen if it is 90 degree? Okay, theta is 90 degrees this side here. This is the normal draw. So you have to put the ball here like this. This is your 90 degree. Yeah, it will simply roll on the surface. Roll on the surface. Rolling, we will try to study in our rigid body dynamics. That will also come up. I think next class is that. Okay, when we'll be studying about the rolling motion as well. Rolling motion as well. But for time being, we will not do that. Okay, which slide you mean? Last slide when you say the this particular one, or the previous to this one? Okay. Now, I just need to actually discuss about one problem type, which I should have done earlier itself. This is on the idea of conservation of momentum itself. There are some cases to be worried about. One is firing bullet from a gun. So if you have actually a gun here like this, yeah, and let the mass of the gun be equal to mg, and then there are some bullets which are fired from this, which is moving with velocity mb. Okay, and also has a velocity here given to be ub. Now you have to find out what is the recoil of the gun. Recoil of the gun. Let the velocity here of the gun be equal to vg. Then it can be shown that from the conservation of momentum, that mg vg will be equal to minus of mb ub. mb ub. So vg therefore will be equal to minus mb by mg into ub. So this in fact is called as the recoil velocity of the gun. Recoil velocity of the gun. B. Okay, let's look at one more example, which I think is very, very important. Let's say that I have a platform here like this. This platform can very smoothly move on a surface. This platform has a mass m. Now let's say that a man of mass small m will start walking on the platform with velocity v0. This v0 generally is with respect to the platform. Now when man starts walking here, platform will start moving in the opposite direction with some velocity v. Now the question generally is find velocity v. It may appear to be a very straightforward problem like a bullet and a gun problem, but there's a little issue here. The issue is that the relative velocity of man with respect to the platform is what is given to be v0. In other words, velocity of the man with respect to the platform is v0, or vm minus vp is equal to v0. So please remember that, and you'll be able to solve the problem easily. And therefore, what is the velocity of the man equal to? Vp, by the way, is given to be v. Okay, and therefore velocity of the man will be equal to v0 plus v. Now use this idea and then apply conservation of momentum. It becomes very simple. Now here it says conservation of momentum will be mass of the man into the velocity of the man plus mass of the platform into velocity of the platform should be equal to 0. Or in other words, I get this to be m into, this one here, correct, V naught plus V plus mv is equal to 0. Or in other words, what will be the velocity here? I can obtain this as mv naught plus m plus mv is equal to 0, or v will be equal to minus m naught by m plus m. A very, very important idea, I would say. This is something which will distinguish you from ordinary students. The students who don't use this idea will be making a mistake, but you should not make a mistake, and you should have an advantage over others. And this is going to be something which will help you to do. Okay, so a problem where one body is moving on the other body, please use this idea to get the answers. Okay, I think now we are in a position to go to MCQs. Have you all written down this? If you all have written down this, then I'll go to the MCQs to be solved today. So since I got some S's from many of you, I'm now going to my MCQ part. Okay. Let's look at the first problem. An explosion breaks a rock into 3 parts in a horizontal plane. 2 of them go off at right angles to each other. The third part of mass 1 kg moves with a speed of 12 meters per second, and the second part of the mass 2 kg moves at 8 meters per second. Okay. If the third part flies off at 4 meters per second, then its mass is. Okay. Very interesting problem. They both, in fact, are breaking into 3 parts in a horizontal one. First one is 1 kg. Moving at 12 meters per second. Second one is 2 kg and moving with 8 meters per second. If the third moves with 4 meters, then asking you what the mass is. Okay. Now the first 2 is at right angles. Okay, first 2 at right angles. And so if I solve this problem now, let's see what we get. Let's see what we get. That will be a case of I thought I'll write down this basically a diagram here for this. First one is of 1 kg, is moving with 12 meters per second. The other mass is 2 kg, and moving with a speed of 8 meters per second. Now, third one should move in such a way that the net momentum here should be equal to 0. That is, P1 plus P2 plus P3, all are vectors, mind you, should be equal to 0. Or in other words, I can say that P3 should be equal to minus of P1 plus P2. So vector sum of P1 plus P2 you take. It will be somewhere here. So you will find that the third particle is going to move. Third particle is going to move like this. What is the mass of the third particle? Is to be determined, m, but it's moving with 4 meters per second. 4 meters per second. So what I can therefore say is the magnitude of P3 should be equal to the magnitude of P1 and P2 put together. So should be equal to magnitude of P1 and P2 will be P1 square plus P2 square. So P3 is given to be 4 times m. I don't know what m is. I have to find out. I only know its speed. What is P1? P1 will be 12 into 1. So should be equal to 12 square. What is P2? P2 is 8 into 2. So P2 will be equal to 8 into 2 is equal to 16. Okay, so it becomes 16 square. 16 square. Now, if you take 4 square outside this, I get this to be 4. into root of, if I take 4 square outside, this becomes 3 square, isn't it? That becomes 9 square, plus 1 4 is gone here, so it becomes 16. So what will this be equal to? I'm sorry, I think this is 9. This is 9, isn't it? 3 and 3 is there, so it's 9 square. Huh? No, it's 3 square. Yeah, 3 square plus 4 square, and therefore this will turn out to be 4 into 5. 4 into 5. So this will be 4m. So m therefore should be equal to 5 kg. Should be equal to 5 kg. So the answer to this is second one. The second one. M is equal to 5 kg. In fact, is the right one. Is the right one. Try to be careful. It's a vector which is to be obtained. All right. So this is how I can basically write down the conservation of momentum in the 2 different directions and work it out. Second question. Second question. Okay. In a gravity-free space, so there is no gravity here. So which means G is equal to 0. A man of mass m standing at a height h above the floor throws a ball of mass m straight down with a speed u. Okay. So man is standing at a height h, Then what he does is he's going to throw a stone of mass small m. His own mass is capital M. Okay, throws a ball with a velocity u. When the ball reaches the floor, that is when it comes to this point, the distance the man above the floor will be. Now look at it, by the conservation of momentum, if he throws the ball like this, man is going to move here like this. And then he will go to a point where it will be at some height here, which you can take it as something like h dash. Okay, when this ball comes to this particular point, h. Ball has come down to the floor. Now where is the man? For this, I'll be using the idea of conservation of momentum and then tell you a very simple idea. Here you will find that m into h dash should be equal to small m into h. You can be sure about that. So you will basically have this h, m into h. That is the displacement of the mass is small m is h. This is capital M is h dash. There is no gravity here. Please mind you that. There is no gravity. And hence you will be able to show that m h dash will be equal to mh. Or h dash in other words will be equal to m by m into h. Now, what is the total height of the man? That is what is being asked in the problem. What is this height of the man given to be? So to which he is present. So the total height therefore will be equal to h plus h dash, which will be equal to h plus m by m into h. Just see which one actually gives you the right answer here. So h into 1 plus m by m. 1 plus m by m. Remember, greater the mass that he takes and then throws, greater will be the height to which he can go. Okay, it depends on that. So the first one should be the right answer to this. Wonderful. So 2 questions basically testing you on the idea of conservation of momentum. Very nicely done. Okay, very nicely done. Third question. 3 particles A, B, C of equal masses move with equal velocity v along the medians of an equilateral triangle. Okay, like this. Now, when the 3 of them are coming, so PA plus PB plus PC, what do you think will be the net momentum in this case when the 3 particles are coming towards each other like this? Which one you want me to repeat? Srinivas and Karthik? Which one you want me to repeat? You want me to repeat the previous one, is it? Okay, second one. Okay, I'll just spend a little time for someone who is asking me to repeat this second one. See, there is actually a gravity-free space. A man of mass m is throwing a stone of mass small m towards the floor, because of which he is going to rise up. Okay, to a height h dash. I've taken that as h dash. Now, because of conservation of momentum, you can show that capital M into V will be equal to small m into u. Now, in a given duration of time t, you can say that v into t will be equal to m u into t. I can multiply time on both sides. What is v into t? Is h dash. What is u into t? Is h. And therefore, I'll have mh dash is equal to mh. So the height to which the man has gone from this particular point is m by m into h. That is what I took here. And the total height will be equal to h plus h dash, which is h is equal to m by m into h. So I get the total height to be equal to this. Okay, total height is given by this quantity. I hope I made that point clear to you. Problem number 3. So I was asking you this question. If the momentum of each of the particle which is coming here towards the center is all same velocity, same masses, what will be PA plus PB plus PC equal to? Okay, you will find that you have 3 vectors which are essentially of the same magnitude. Okay, essentially of the same magnitude. And from Lamy's theorem, you can show that the sum of the vectors here should be equal to 0, because look at it, the angles are all same, 120 degree. Okay, and also the vectors magnitudes are same, and therefore the sum of them will be 0. So what you can say is initial momentum of the system, is 0. They collide at the center O of the triangle. After the collision, A comes to rest. Very nice. B retraces its path with velocity v. So B is coming back here with velocity v. A will come to rest, will not move at all. The velocity of C then is very interesting. Initial momentum is 0, right? If initial momentum is 0, final momentum also must be 0 according to conservation of momentum. So what is after collision happening? B is coming like this. Okay, mass with mass m and velocity v. A is coming to rest, it doesn't contribute. So now where will the C therefore go? C has to go in the opposite direction so that the net momentum will become 0. So C therefore should be moving opposite to B. Now what is it opposite to B here? It should be moving from B to O. We'll have the same velocity and will be moving from B to O. So therefore the answer should be, it has a velocity V and direction is B to O, from here to here, like this. So the collision has to be in this way. Collision has to be this. 4th. Okay. The theorem basically is called Lamy's theorem. I hope you all know about Lamy's theorem. In vectors, we used to do this. And you also have done an experiment on this equilibrium, okay, or called as the Lamy's theorem experiment itself. If I have, say, 3 forces, P, Q, and R. Oh, I'm so sorry. I think the arrows should be like this. Arrow should be like this. Arrow should be like this. All right. Now this angle, let's say, is alpha. This angle is beta. This angle is gamma. Then, if this is point O, O is in equilibrium. Equilibrium is the net force will be 0. Equilibrium when P by sine beta is equal to R by sine alpha is equal to Q by sine gamma. Then we have this to be in equilibrium. Now compare this with this particular part. Here the angle between each of them is 120 degree and each one of them has the same momentum. So P by sine 120 is equal to P by sine 120. Now if this is satisfied, then what should happen to the net say equilibrium or the net sum of all the vectors here should be equal to 0. Okay, that is why I said that the initial momentum must be equal to 0. Is that idea clear? Can I get your response and then I'll move on? Is this idea okay? Someone asked me to explain the theorem, the Emmys theorem. Okay, fine. Fourth question. I think you can answer this question yourself. We have done this fourth question as a special case. A ball is projected with an initial velocity on theta to the horizontal. The horizontal displacement covered by the ball as it hits the ground after the third time would be after 3 times. So this is your first time. Okay, second time, third time. After the third time. So I need R0, R1, R2, R3, isn't it? Ground as it hits the ground the third time. So I just want up to R2. I'm sorry. So therefore, this should be equal to R equal to the range horizontal range x is equal to R0 plus R1 plus R2. You don't have to take R3 on, right? Because as it hits the ground the third time. Because it's after the third time, I don't need to consider only up to here. So I need to find out this distance here. This distance here, x. Okay, that will be equal to R0 plus this. We know what this is, R0 plus E times R0 plus E squared times R0. And therefore, x will be equal to R0 into 1 plus E square. 1 plus E plus E square. Very good. I think many of you are saying that is the fourth one. You're right. It should be equal to U square sine 2 theta by G into 1 plus E square. Perfectly all right. So fourth one is the right answer to this question. Okay. Let's do fifth question now. A ball of mass 1 kg strikes a heavy platform, perfectly elastic, heavy platform. Okay, keep an eye on this. Moving upwards with a velocity of 5 meters per second. The speed of the ball just before the collision is 10 meters per second downwards of the ball. Then the impulse imparted by the platform on the ball is. Nice question. It actually combines 2-3 ideas, so we will try to work it out. This impulse can be calculated by finding what is the change in momentum. Change in momentum of the ball. So the change in momentum I will write as PF minus PI. This will be the impulse. Let's see how to find out this. So I should know what is initial momentum of the ball. That is easy to find out. It's 1 kg. 1 kg into what? Into 10 meter per second. So it should be equal to 10 Newton second is PI. But what is PF? That I have to find out using the idea of collision. I'll take the mass of the ball to be M1 and platform to be M2. And I know that M2 is much greater than M1 because it's heavier. It's very heavy when compared to M1. So I can use the formula. And I have to find out, look at it, M1 now, V1. I have to find out V1. I'll use the formula. V1 is equal to 2M2U2 by M1 plus M2 plus M1 minus M2 divided by M1 plus M2 into V1, into U1, I'm so sorry, into U1. So therefore, I'll get V1 to be equal to, see, M2 is very large when compared to M1, M2. So this becomes M1 will go away, M2. So this will be approximately equal to 2U2. And what will the second term be? M1 is negligible, so goes away. M2 you have, M2 you have. So M2 is minus M2 divided by M2. So this becomes minus U1, minus U1. So this will be therefore 2 into, what is the velocity of the platform given to you? What is the velocity of the platform? Well, perfectly elastic, moving a ball, platform is moving with 5 meters per second. So U2 is 5. So this will be equal to 2 into 10. Now be careful. What is U1? U1 is coming down. So it should be minus 10. So it should be minus 10. And hence I get this to be 2 into 5. I'm so sorry. 2 into 5. So 10 plus 10 is equal to 20 meter per second. So what is the velocity after collision? Is 20 meter per second. Now I can find out what PF is. PF will be equal to simply mass of the ball, which is 1 kg, into 20 is equal to 20 meter per second. And what is the direction? Direction is upwards. Direction is upwards. Initial momentum, by the way, I was little careless. It should be minus. By the way, what is the minus 10 Newton per second? Meter per second. Now I have to find out what the impulse is. Impulse will be I is equal to PF minus PI, which will be 20 minus of minus 10, and therefore it turns out to be 30 Newton second. Newton second. So the impulse therefore will have an answer which is 30 Newton second. Do we have that option here? Yes, we do have. That is the fourth one. That is the fourth one. So the answer to this fifth question is this. Very interesting, isn't it? There are two parts in this problem. Look at it. One is about the impulse. The other one is about the change in momentum, which has to be worked out in this way. But that formula really helped us in getting this answer. Sixth question. Now, many of you may be wondering as to some of these problems, in fact, are at a little higher level. Yes, expected, because nowadays the CET, especially the physics part of CET, is becoming very tough. It's almost like mains examination. That is why we also have selected a little higher level problems so that you will all get benefited. Okay, sixth question. From a floor of very tall tower, a ball is thrown vertically up with a velocity of 30 meters per second. The roof of the tower is horizontal and is at height of 40 meters above the floor level. The collision between the ball and the roof may be taken as elastic. After how much time reckoned from the moment of throwing up with the ball reaches the floor? A very nice question. A lot of interesting ideas are there, and therefore please make sure that you are attentive while you are understanding this problem. 30 meters per second is the initial velocity. As it reaches a height of 40 meters, remember it would have lost some amount of velocity. Now, what is the amount of velocity that it loses? Can be easily worked out. V square is equal to U square minus 2GH, something that we all know from our discussion earlier. So this becomes 900 minus 2 into 10 into 40. That becomes 800 together. Minus 900 will give me 100 meters per second. So what is the velocity therefore equal to 10 meters per second? 10 meters per second. So I get the velocity with which it's going to hit this will be 10 meters per second. Now it will rebound back. It will rebound back with same velocity, 10 meters per second. Now a collision is only here, which is telling you that it's going to come back with 10 meters per second. And now I have to find out the total time taken, T1 and T2. So let's see how to find out T1. T1 is very simple. I say to find T1 will be equal to, velocity here is 10. Initial velocity is 30. So it should be 30 minus 10 divided by G. G is 10. So this turns out to be therefore 20 by 10 equal to 2 seconds. So T1 is 2 seconds. Very simple to find out. Now I have to find out what T2 is. I have to find out T2 is. Any guesses as to what T2 is going to be? What T2 is going to be? You can actually work it out in the following way. the height to which it's going to come down. So I'll use y is equal to ut minus half gt square to find out the second part. So here this is equal to minus 40, u is going to be minus 10 t, and g is always 10. So it's 10 t square. So you get a quadratic equation with all the things being negative, right? So now if you simplify this, you get this to be t square. This is, I have to write this as goes to the other side, becomes plus 2t. Then this will be minus 8 is equal to 0. So therefore, what is t equal to? T is equal to minus 2 plus or minus this is all right? Yeah, plus or minus 4 plus 32. 4 plus 32 divided by 2. So t also will be equal to minus 2 plus 6 divided by 2. So will be equal to 2 seconds. T2 also will turn out to be 2 seconds. So this also is 2 seconds. And hence the answer to this question is 4 seconds. So what is the time that it takes? Total time will be 4 seconds. 4 seconds. Very interesting. So we have done up to problem number 6. And if you all are okay with this, now I would like to go to my next problem. Can I go to my next problem? Can I go to my next problem? If you all are done with this. Very interesting. Okay. A lot of things to be done. Question number 7. A person weighing 60 kg in a small boat of mass 140 kg, that is at rest, throws a 5 kg stone in a horizontal direction with a velocity of 14 meters per second. Velocity of the boat immediately after the throw is. So there's a boat here like this. And then a man who is standing on the boat. Okay, he is basically 60 kg. 60 kg. Throws a 5 kg stone horizontal direction with a velocity of 14 meters per second. So he's going to now throw it with 14 meters per second, this 5 kg one with 14 meters per second. 14 meters per second, so 5 kg one. Mass of the boat is going to be 140 kg at rest. Velocity of the boat immediately after the throw. So the boat and the man is going to move with some velocity v. So I have to find out that. So I get this to be therefore 5 into 14 should be equal to, because m of the stone with velocity should be equal to mass of the boat plus mass of the man into this velocity. I'll call this as u, all right? So then I can call this as v. So 5 into 14 is equal to mb plus mm. So 140 plus 60 into v. So therefore, you can find out what v is. This turns out to be 200, isn't it? Turns out to be 200. So 5 into 14 divided by 200. So this will turn out to be 0.07 into 5. So 0.35 meter per second. 35 meter per second. So the answer to this should be third one. Quite easily done. No issue at all. It's just the conservation of momentum that has to be done. Okay. A moving block having mass m collides with another stationary block having mass 4m. The lighter block comes to rest after the collision. When the initial velocity of the higher block is v, then the value of the coefficient of restitution E will be equal to. Okay, will be equal to. Nice question. Oh, wonderful question, I would say. Let's see how to work out this. Now, the coefficient of restitution comes in your idea of V2 minus V1 is equal to E times U1 minus U2, isn't it? U1 minus U2. The first body, which actually has a mass m, is moving with a velocity v. The initial velocity is v. So U1 here will be equal to v. Initially, the second body is stationary. So U2 will be equal to 0. So hence I get this to be E times v minus 0. And after the collision, what happens? The first block will come to rest. So 0. Okay. Now, V2 therefore will be equal to this. So V2 minus 0 is equal to this. Or in other words, I get V2 to be equal to E times V. All right. Keep this idea in mind. This I got it purely by applying Newton's law of collision. Now, if I apply conservation of momentum to this, I get this to be m into v is equal to 4m into v2, 4m into v2. Or in other words, I get v2 to be equal to v by 4. Now compare the two equations. Compare the two equations. You compare this equation with this equation, with this equation. Now, if you compare the two equations, 1 and 2, you get the value of E to be equal to 1 by 4. E equal to 1 by 4. E equal to 1 by 4 means 0.25. 0.25. Yes, many of you are giving me that answer. I'm very, very happy about it. Okay. Ninth is a straightforward question, right? A ball is thrown on a smooth horizontal surface of coefficient of resolution E for the ball with a speed u and angle theta with the normal to the surface. It leaves the surface at an angle phi. You have to find out what that phi is. Tan phi should be equal to 1 by E times tan theta. Of course, there is a minus sign there, but I think we'll not worry about that. Okay, because this angle is already shown, so you just have to find out the magnitude of it. Magnitude of it. So what should be the answer to this? Answer is this. 1 by E times tan theta. E times tan theta. Okay. So good. So we have done up to 9. Let's now go to the next set of questions. If you are done with this, let's go to the next set of questions. A body of mass 4 kg moving with a velocity of 12 meters per second collides with another body of mass 6 kg at rest. If the two bodies stick together after the collision, the loss of kinetic energy of the system is. So to find out what will be the loss of kinetic energy, I told you how to work out problem of this kind. Now use conservation of momentum. Now what does it say? That the initial momentum, which is 4 into 12, okay, the second body is at rest, so 6 into 0 should be equal to 4 plus 6 into v. So that will turn out to be 12 4 is 48, and this will be equal to 10 times v. So v therefore is equal to 4.8 meter per second. 4.8 meter per second. Now I have to obtain the loss of kinetic energy. The loss of kinetic energy will be equal to initial kinetic energy minus the final kinetic energy. Initially, it is half 4 kg into 12 square. After the collision, it is half into mass is 10 because 4 plus 6 together will be considered. Moving with a velocity of 4.8 the whole square. 4.8 the whole square. Now simplify and get the answer to this. So this will be half of 4 into 144. Okay, minus this. This will be 10 into 4.8 the whole square. What will be 4.8 the whole square roughly? This will be like 4.8. So 4 square is 16. 4.8 into 4.8. We'll have to very quickly do this and see. 4.8 into 8 will be 8 8s are 64. 8 4s are 24. 24 plus 6 is 30. 30. So 3.4. 3.4. Okay, 3.4. And then 4.8 into 4 would be 32 is 2, 3, 6, 9. So this would be 19 point something, 19.2. 19.2, correct? 19.2 plus 3 is 22.2. So this will be 22.4. Okay, is what I get this to be. 9.6 is what I get this to be. Or this will now turn out to be 4 into 4 is 16. 16 plus 1, 17. 17. And then I have 17. So I have 1. 4 ones are 4 plus 5. 576 minus 226. Okay, half of that should be the answer. So delta K will turn out to be whatever you get this to be here. 172.8. 172.8. I think roughly around that. I think you can easily see from there itself. Say from here itself. Okay. I have made some approximations, of course, so that it becomes easy for you to work out. 11th question. A body of mass m hits normally a rigid wall with a velocity v and bounces back with the same velocity. The impulse experienced by the body is. Impulse again is essentially same as the change in momentum. Here it is moving with a velocity v, so its momentum is going to be mv, like this. When it comes back, again it's coming back with the velocity v, and therefore once again it will have the same momentum but in the opposite direction. So the change in momentum, impulse which is same as change in momentum, should be equal to mv mv minus of minus mv, and that will be equal to 2mv. 2mv. So therefore it should be, answer should be 2mv for this. So that's the 11th one. 11th question. 12th question. I think we'll end with this. A particle of mass m moving with velocity u makes yes, ma'am. Ma'am, I'm in the class. You want to say something for the class itself? I don't mind taking it now. Okay. Okay. We'll see what to do. Yeah. A particle of mass m moving with velocity u makes an elastic one-dimensional collision with a stationary particle of mass m. They are in contact for a very short time t. Their force of interaction between 0 to f0 is linearly in time t by 2 and decreases linearly with this. The magnitude of f0 is, okay, magnitude of f0 is. It's a nice question to really answer. So to this, you just have to see what will be the change in the momentum, because see, this is the impulse. This is the impulse, and that impulse can be written as you can see, half into f0 into base, half the base into height. Base here is going to be t. That should be equal to the change in momentum. A particle of moving with velocity u makes an elastic collision with a stationary particle m. They're in contact for a very short time, and then they basically will move. So as a result, the change in the momentum will be equal to m into u for one particle, right? Initially it was there and then it came to rest. It came to rest, so mu. So f0 therefore should be equal to 2mu by t. 2mu by t. So the answer to this is 2mu by t. With this, I'm stopping the discussion because I'm taking more time now. You have one more class after this, 2 more classes after this. So another 3 problem is for you to solve. If you don't get it, I'll be very happy to solve them in the class. Okay? Or shall we? No, I think there are 3 more. We shouldn't really stretch too much. So I think I'll stop with this. 3 are very simple. You'll be able to do it well, easily. I'm sure about it. So do it. I'll be sending this notes and also the solution to this problems. Okay, you can therefore have both of them. The questions and the answers will be there with you. Thank you very much. I hope it was useful for all of you doing this. So see you all next time. Next time I'll be looking at the circular motion.
Can I close?